Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 51 and in this we will be looking into interfacing quantum processor with classical controllers. So, in our previous discussion we had seen the block diagram for the quantum processor and we saw that the qubits are sitting at millikelvin and you will have mux and demux sitting at millikelvin, and there will be the readout circuitry will be typically at 4.2 to 10 Kelvin, and the back end circuitry, the control circuitry from the external source will be at 300 Kelvin. Now, we look at this CMOS readout circuitry here. So, this is an optical readout circuitry. So, I have an avalanche photodetector here which basically collects information about the qubit state, amplifies the signal. So, this basically is APD which amplifies the signal, right, amplifies the signal, sends through an amplifier, sends it to a readout circuitry. This is a time to digital converter which converts these analog signals to digital signals. Then in the control part you have an ADC which converts these analog back to digital. Then you have a mixer here and a LNA, and these mixers and LNA help you to again. So, there are two readout paths which is available, one is the TDC path, one is the ADC path. Now, the primary goal of the readout circuitry is to accurately capture the information which is possessed in the qubit state without introducing any noise or significant errors. Now, let us go one by one. Let us look at the avalanche photodetectors. They are primarily used for detecting optical signals and then converting the photons into electrical signals. So, typically if you look at its structure, it basically tries to generate avalanche of electron hole pair, and this avalanche of, so that gives you a certain spike in the output current, and from there you can predict the state of the energy and the state of the output photon. Then you have an amplifier which basically boosts the weak signal without adding any significant noise. So, typically you need to understand this amplifier is primarily a low noise amplifier and also helps you to generate low noise and amplify to a larger extent. Then TDC is another is time to digital converter which converts timing information of the signal into the digital format. We have low noise amplifier which amplifies the signal while minimizing the added noise. So, the LNA will have a larger SNR at the output side as compared to the input side. Finally, the ADCs will be required because all the signals which you get in the input side will be all analog signals and all the processing will be done at digital level. So, there will be ADC, but please keep in mind that all these active devices are typically kept at relatively a very low temperature, and a cryogenics which is 4.2 to 6 Kelvin temperature they are kept, and therefore their functionality might get drastically affected as we have discussed in our earlier lectures. Now, as I told you that if you look at the components of the cryogenic CMOS readout circuitry, and this is the gain versus the frequency basically, and you see that quite interestingly that, so the room temperature is the red one is the room temperature, this is the room temperature, this is at 77 K and this is at approximately 4.6 K. So, the room temperature of course has the largest bandwidth, but it has got a reduced gain, and then 77 K is where your bandwidth is also reduced, but the gain is relatively high. And at 4.6 your bandwidths are very much minimized and the gain is intermediate between the room temperature and at 77 K. As I discussed with you, there is that APDs are detecting the signal and trying to put in an amplification out of it. Now, the amplifier should be strong enough so that the signal which you are generating at the output amplifier will be able to drive the external resistance or external load in a proper fashion. On the right hand side, if you see clearly, your bandwidths are basically restricted at 4.6 Kelvin, right, they are pretty low, and that is one of the major issues which you will face while dealing with cryogenic CMOS readout circuitry. Now, let us look at the ADC, and the part of the ADC is basically a TDC. If you are looking at on chip realization, then basically ADC is used on the FPGA. It comprises primarily of a voltage to time and time to digital converter in cascade, and the primary reason is that you need to convert the analog signal to outputs into the external signal. Now, if you look at, this is the start stop signal of the TDC here. When the signal starts, there is a input count which comes into picture, and depending upon the input signal, between the start and stop the output will be generated, right. So, the V out is basically the reference output voltage which you are able to generate, and with respect to V reference, and R reference is the resistance offered by the design. So, this is what you get, and then the typically LVDS, if you see, you will get almost like a shark fin ramp voltages which you will get in the output side at this particular point. and this is a time domain, it is a very regular signal, and the TDC actually starts to sample those signals in timestamp T1 to T2 and then tries to extract the digital component out of it. Now, the TDC, let us look at the signal processing and the conversion in cryogenic CMOS. The TDC is basically time to digital converter, and it converts signal timing to digital data, we have seen that, and it ensures that the precise measurement of gates and operations are done. Please understand that the very idea is that your readout circuit should be so robust that it should not affect the state of the qubits while reading it, right, and therefore it is very important that whatever design is done in the readout circuitry should be such that it does not destroy the state of the multiple qubits which are there in the millikelvin region. And there is always a temperature gradient between the millikelvin region and the readout circuitry, approximately 10 to the power 3 Kelvin change, right. Now, what is the need for a precise timing in quantum computing? Now, the quantum states needs to be predicted at very specific times, right. If you do not do that, you might actually be predicting wrong states of information while you are handling the quantum computing purposes, and therefore accurate timing actually minimizes the error, and therefore decoherency is minimized and incorrect results are minimized in case of TDC. Now, if you look at the final output, we are basically looking into the digital signals. So, after your signals have been amplified, they have been going through TDC, and you have a digital output being done, the output is primarily a digital signal, and that represents the information from the quantum processor. So, a particular state of the qubit will be matching with the output, digital output, right. When you change the state of the qubit, the digital output will go on changing. So, finally, we need to do a one-to-one correspondence between the state of the qubit and the digital output which you see. Now, the digital output is then fed to control circuits, which might include, for example, an FPGA or an ASIC for further processing, error correction, and finally the eventual output may be sent to other parts for the storage purposes. As I discussed with you, need not to say that the integrity of the quantum states and ensure that the readout circuit performs with the highest possible fidelity, right. Now, all these processes are conducted at cryogenics. So, these are all performed at cryogenic temperatures, and you need to ensure that the readout circuits perform to the highest fidelity. Fidelity primarily meaning that there is a one-to-one correspondence between the signal given to the system to read it and the output which is getting from the cryogenic systems. Now, this is again the diagram I am repeating it, which we had done in the previous lecture, and what we do is that you basically deliver precise electrical signals to manipulate the qubits, and therefore they allow you to do some quantum operations, right. So, the qubit control also responsible for fixing the qubit states and initialization of the qubits, manipulation of qubits, and the readout of the qubits. So, three stages, important 3 stages happen in this case with your initialization, manipulation, and readout. So, all these 3 are being performed by the CMOS circuits and system at the cryogenic. Now, signal processing amplifies weak qubit signals with minimal noise, right. That is what the idea is, and also handles the control and readout signal routing between the quantum and classical system. So, please understand that this is your quantum state, this is the quantum state, and this is your classical electronics, right, which is at cryogenic. Now, this part is basically the interface between the two, right, and therefore, in this interface you have to be very careful about the type of signal which you are getting at these interfaces, right, and that is pretty interesting and requires a good amount of preciseness and fidelity. Let us give you a first small example about the DAC, or a digital to analog architecture converter. It is an 8-bit current steering DAC, which is basically, so the currents are here I1, I2, I3, I4, and this is the MSB, this is the LSB which is being pointed out here. You send the input code here, right. So, we have got 4 LSBs and 4 MSBs, then you do latching, and then latching we try to do an on-chip current reference here, which primarily means that you latch what is the current source available at each of the bits, and then they are integrated on-chip current reference sources. Now, typically this is a 4 MSB plus 4 LSB segmented current steering DAC output which I am showing here. The only problem with such type of current steering DAC architecture is they are quite power hungry, because you need to generate these band gap references, current sources and multiple number of times. So, if there are 8 bits available to you, you require 8 independent current sources which are basically extracted from band gap reference nature, right. So, that is sort of a cost you pay for much accurate value of the DAC architecture. Let us look at the auxiliary circuits. The auxiliary circuits, if you look very carefully, you have a thermal sensor which is basically a temperature sensor, this one, right. These are auxiliary circuits which are not part of the, they are part of the readout for sure, but they are not primarily used for reading out, they are more of a circuit to take care of the auxiliary units which is maintained within the qubit. So, this is a temperature sensor which monitors the temperature of the system. We have voltage versus current references. These provides stable voltages and current references, and they are very critical for circuit operation. And the purpose is primarily to ensure that the system operates efficiently, right. And so, if you look here, this is IV references, these are all maybe band gap references which you use, and these band gap references are responsible for giving a fixed value of voltage and current independent of the ambient which you see. Now, so this auxiliary unit, depending upon where the switch, so these are basically switching caps, switching circuits, and these switching circuits can be attached to this or this or this. When it is attached to this, a frequency generator comes into picture. When it is attached to the second one, it goes to the grounded, and when it is the first one, you have an oscillation circuit available, and you require a stable oscillator being generated in the auxiliary circuit. Okay. So, let me come to the temperature sensor now one by one. So, this is the right hand side is basically a basic diagram of a temperature sensor, an op amp based temperature sensor, and this ensures that the temperature at which the readout circuit works is maintained stable around 10 Kelvin, 4.2 to 4.6 up to 10 Kelvin, it is maintaining a stable temperature. This will give me a real time temperature range, the range of temperature will be given by this auxiliary unit, and primarily depending upon the value of these calibrated resistances which are shown here and the reference resistances F1, F2, F3 shown here, you will get typical value of VBT, voltage at temperature T, and it will be fixed. So, it is basically when you say SW3 is switched on and this is W3, the same switch is switched on, RCal3, R calibration 3 and RF3 gets activated, right, and you will have some sort of an inverting amplifier in this case available to you. Since RBT is basically the bias temperature temperature based resistance, as you change the temperature, this so the resistance changes in this manner, that R equals to R naught 1 plus alpha delta T, where alpha is basically my thermal coefficient. If you multiply with delta T and you multiply with R0, I will get the total value of R. R0 is basically the resistance at the ambient. Now but again the disadvantage here is basically linearity of the switch and the power consumption of the switch, which you need to take into account in this case. Moreover, when the switch closes, you basically are able to transfer charge either on the inverting node or the output node of the op amp here. This is the op amp which I am referring to here, right, and that gives you some spikes at the output as far as CMOS temperature sensors are concerned. This is a band gap reference which is available to what? This is basically a voltage or a current band gap reference. We also refer to as V/I, and supplies, these are consistent supplies voltage and current levels to various parts of the circuitry, and they maintain accuracy and stability of the entire cryogenic system. It is very important sort of block in the CMOS auxiliary unit, right. And this is basically a BJT BiCMOS technology. So, I have a BJT at the top Q1 and Q2, and I have loads as PMOSs as P1 and P2 maybe here, right. So, it is consisting of Q1, Q2, P1 and P2. So, there are 4 transistors which are available. These Q1 and Q2 are BJTs, bipolar technologies, and P1 and P2 are basically your PMOSs which are responsible for maintaining the stability. Now, why is it important to have this is again to maintain a fixed temperature at the output side, current or voltage at the output side. Then within this we also do a frequency generator, and that is basically using a PLL or a phased loop lock here, right, and it stabilizes the, and what is the main problem with oscillator is the stability of the oscillations at such a low temperature. and this PLL system helps to stabilize the oscillations by adjusting the VCO gain, right, based on the reference signal. So, you have a reference signal coming and you have a main signal coming. You try to basically reduce the error between the reference signal and the input signal, so that a stability is achieved as far as PLL system is concerned. And the whole idea is to do a good amount of frequency locking and also to minimize the phase noise. Phase noise is a big noise in a phase lock loop. Okay, so if you look at the basically a free running VCO, if you look, this is the free running VCO and it goes down, you see the phase noise is directly proportional to, or like inversely proportional to the offset frequency. However, in case of locked PLL, the noise remains almost, phase noise remains almost constant, and it is independent of the applied offset, which is not true in case of a free running VCO or a voltage controlled oscillator. So, this means that my phase noise is almost removed in this case. However, please understand one important property, that most of the cases whenever we design PLL, and if for that matter any oscillator which is phase lock loop, in this particular case, you need to ensure that the phase noise or the thermal noise is as low as possible, because in any way your signal is so small that if your signal floor and the noise floors become very close to each other, there will be a big problem of segregating these two signals and how to filter out these signals. So, one way to do that is keep your noise floor very small as compared to your signal floor. So, it might even go up to femtovolts as low as that, the average value, the RMS value. So, let me recapitulate what we did till now. We had discussed about the basic idea about the readout circuitry, right, readout circuitry. We also looked into the various functionalities of the readout circuitry, right, and we also understood how these circuits can be maintained at room temperature and at 77 K and at 4.6 Kelvin, right. So, this was what we had done, at least for these courses. Basic electronics will suffice, and we try to keep the noise as small as possible, so that the signal to noise ratio is maintained at a very high value for even at these noise voltages. Now, let us switch gears and come to the quantum gates, right. So, what we will study now is, in the next set of design we will study is what are quantum gates and what are single qubits gates, what are the operations and universality of making a logic. So, now if you remember, just as we were doing in a ordinary digital electronics course where we study say a NAND gate or a NOR gate, we will do a corresponding study of the quantum gates for the purpose of quantum operations. Now, let us look at first of all what are quantum gates and what is the key difference between the quantum gates and classical gates. Now, the classical gates are irreversible, right, which means that once you put input bit, you will always get output bit with you. However, the output bit which you get might be not a one-to-one correspondence with respect to input, right. Say for example, you are doing a NAND gate, then if you look at the truth table, then you can have in the NAND gate for 1 1 it will be 0, but for 0 0 it will be 1, and then for 1 0 it will be again 1. So, you will have multiple 3 1s and 1 0 for a 2 input NAND gate, right, which means that the output is, just looking at the output you cannot predict what the input is. You can have 1 1 1 0 0 1, whereas similarly NOR gate you will have 3 ones again available to you, right. So, this is irreversibility, whereas quantum gates are reversible and they follow primarily unitary operation. So, no information is lost. So, there is loss of information is very low or almost impossible if we are handling this quantum gates. Let us look at state handling. Classical, as you all know, classical gates operates on bits. So, you can have a 0 or a 1, and you are very much aware that the 0 and 1 is by absence of a pulse, or a presence of a pulse is defined as 0 or 1. Quantum gates operates on qubits, which, and therefore these qubits can be a superposition of zeros and ones depending upon the state of the system and the weight which is applied to 0 and 1. Typically, generally all my quantum states are referred to by unitary matrices and also referred to as identity, and basically it is u multiplied by u cap, right, where u cap is basically the transpose of u, right. So, if you know the unitary matrix for any input, I can find out u cap. When you know u cap, you can find the value of the u into u cap, therefore will be always a unitary matrix. These are the single qubit states, and these are very straightforward gates which are available. So, these are poly X, poly Y, poly Z, and then you have a Hadamard gate, and then you have a phase gate, and you have a pi by 8 gate, right. So, these are the matrix which is involved. So, this is referred to as X, poly X, this is poly Y, this is poly Z, this is Hadamard, this is phase, and this is time, right, pi by 8. The matrix associated with that. So, the most common examples of matrix usage are basically these 5, this and the phase, right. So, Hadamard X, Y, Z, H, X, Y, Z, H, and Hadamard. Hadamard is, so H is the Hadamard one which we are talking about, right. So, typically these are the most often used gates in the design. This one is the most often used gates, and as I told you, there is a matrix representation on the right hand side. So, whenever I insert, let us say, a poly X gate onto a system, I basically insert matrix whose principal diagonal is 0 0 and the off principal diagonal is 1 1. So, it is a unitary matrix which we are doing it. So, when we multiply the gate matrix, this gate matrix with the initial state, which is the column vector or the Dirac notation, we get the final state. So, you multiply with a column matrix with the Q matrix. Let us look deep dive into what is an X gate, which is a Pauli X gate, also referred to as. The symbol is given by this, and the functionality primarily of Pauli X gate is it flips 0 to 1 and 1 to 0, and it is complement, and it is the analog is the analog of the Pauli X gate in digital logic is basically the NOT gate, right. Now, what does poly gate do? Poly gate, which is a Y gate, it not only shifts, the symbol is 0 0 by principal diagonal, and minus 1 1 is there. So, this what it does is that this only not only shifts the flips the state, but what it does is that it also tends to change the phase, introduce a phase shift. So, there is a flipping of the state as well as there is it introduces a phase shift within the state itself, right. And so, how do you see the phase shift? By the block sphere. From the block sphere, the vector will change, and you can actually predict the phase shift because application of this Y gate. And now, let us say, for example, an example of Y gate is it performs a bit flip, as I discussed with you, and let us say a 90-degree rotation around the Y axis in the complex plane. Therefore, we write down Y 0 equals to I, which is a complex quantity, into 1 ket, and similarly Y ket 1 is equals to minus 1 ket 0, right, and that gives you not only a flip, but also gives you a 90-degree rotation in a clockwise fashion. You can also do an anti-clockwise fashion. The symbols will change for these cases. When you look at poly Z gate, it is the principal diagonal is now 1 minus 1, and the off principal diagonal is 0 0, and it introduces a phase flip. So, till now we were looking at poly gate, which was only responsible of, not only responsible for phase flip, but also the transformation of the basis states. Whereas, when you look at the poly Z gate, it flips the sign of the positive 1 gate. So, this flips the sign here. If you look carefully, here also it flips the sign, but it adds a complex conjugate number I here, right, and this therefore gives you a rotation also. Whereas, the poly Z states does not touch 0, the 0 part remains the same, but the 1 part, ket 1 part actually changes to minus of 1 part, and therefore, it flips its state. Let us look at the Hadamard gate, very used very often, and this basically, this is the symbol which you use, H is equals to 1 minus 1 and 1 by root 2. So, if you look, this basically creates a superposition. What it does is basically is that when you put 0, right, when you put a 0 here as the as one of them, then that comes out to be, it is basically a superposition. The 0 state is defined as 1 by root 2 average of 0 1 and 0 and 1 ket vectors, and one state is 1 by root 2 0 and 0 minus 1. So, this is 0 plus 1, this is 0 minus 1, and the root 2 is coming from the fact that it is 1 square plus 1 square root over, and that is root 2. So, effectively I get, and this has been widely used for understanding the equal probability of state, right, and that gives you a quite an interesting idea about what the probability of the state will be. Okay. And now, let us come to the S gate or P gate, and the S gate has got 1 I, the complex conjugate I complex quantity I at the principal diagonal and 0 0. What it does is that it adds a phase of pi by 2, right, and it adds a phase of pi by 2. For example, if you look at this, it does not, for example, in this state it does not change the state of 0 0 ket, but one state is changed by a factor of pi by 2, right. It adds a phase to it, and it is used for quantum interference and phase control. Let us look at pi by 8, also referred to as T gate or Tripoli gate, and it is 1 e to the power I pi by 4, and 0 0 is the off principal diagonal. And if you look, previously it was adding pi by 2, now it is this phase is pi by 4. So again 0 vector is not changing, but the 1 vector is multiplied by e to the power I pi to the power 4 by 2, and they are used in consonance with C naught gate or H gate for quantum computation purposes. Now let us look at the quantum gates and its operation. You have multi-qubit operations involving control operations, and one qubit controls the behavior of other qubits. That is the sort of connecting issues between them. Now these gates are represented by line connecting the qubits which are involved in this thing. So if you see, the control gates are C naught gate and CZ gate, let us suppose. So this wire which you see in front of you, this one and this one, these are primarily the controlling line connecting the two qubits. Now a black circle indicates quantum qubit, control qubit, and which triggers the operation. So if you look at this, this is the black circle which you see here, and this is the black circle which you see here. The target qubit is labeled with a unitary gate. So this x and y are labeled as unitary gate, and the operation is only applied when the control qubit is in state 1. So whenever it is in state 1 and you want to change the phase of it, because if you look at the previous discussions which we have, nowhere I have changed the 0 weight, it is only the 1 weight which is changing. So here also we are saying that we are applying the external voltage to change the 1 bit. This is a basic example of a quantum C naught gate and a CZ gate. These are control gates. So C naught actually flips the target if the control is 0, right. So if you look carefully here, this is the conventional gate which you follow. So x, y, this is x exclusive or y which you are feeding here. So if this is x, y, I can write down, this is the x input which you are feeding, and exclusive or y is given by this one, right. Y exclusive or x will be given by this one. Whereas if you do a C naught operation, I will get 0 0 1 1 0 1 1 0 for an input. Let us forget about x will be replicating as such, and this will be 0 0 0 1 1 0 1 0, right. So you get 0 1 1 1 1 0, which means that for this state you have 1 1 fulfilled, and for 0 0 you have 0 0 fulfilled, right. And for 0 1 and 1 1 there will be reversal in the quantum qubit, and it only controls y, 0 state it does not able to control. And let us look at the control Z operation, and when you see a control Z operation, these are the qubits which is available to us. The corresponding matrix is given by this here, and if you look at swap basically means it swaps the state between high and low, and the notation is this one, and the corresponding matrix which you find out is given by the right hand side, right, and it gives you quite a decent value of the quantum gates. Now let us look at a quantum measurement, right, and this is a quantum measurement in a circuit, in a quantum circuit. The input to the box is basically a quantum bit, right, and this is the quantum bit I am assuming here, right, this is a quantum bit. This is a measurement I am doing, this is the measurement which is I am doing. However, understanding that this measurement does not influence the state of the qubit, and the output from the box is the classical information. So this is the so this is my quantum information, right. I do a measurement and I translate it to a classical information, and therefore the measurement collapses the quantum state into a definite classical state. As you are aware, quantum states will be highly improbable, you will not be able to see the state, but once you do a measurement, then you are very much sure that either of the two states will happen, and therefore definite classical state either 0 1 will be thrown in the output side. The result which is stored here can be then used for storage purposes at every other place. Let us look at the other parts of the measurement. So this qubit, the circuits operates 3 qubits, qubit 0, 1, 1 and 2, and this is how you do it, is that this is the raw circuit which you see, and this is the annotated space-time layout on the right hand side. I am assuming that, so there are 3 qubits which I am referring to. Initially all of them are 0, and then I am passing it through set of Hadamard gates and doing a measurement for that to get extract the actual value of the signal which is available at these particular points. Now if you look at this qubit 0, I have an edge gate here, and when you do the measurement, this is the classically controlled value of the quantum gates which you see, These are the two NOT gates which you will be affecting, which means that they are opposite in nature, and I can therefore specifically tell you what is the value of x or z in this state. Now, the operation is that first of all you apply a poly y gate, right. Poly y gate is applied. When you apply a poly y gate, there will be a shift in the logic, and then step 2 you apply a C0 gate. C0 gate basically controls qubit 1, and that what is the target qubit is 0 qubit. So, you are basically inverting in a sense the qubit, and then Hadamard gate is applied to H qubit. This is the Hadamard gate which you applied to qubit, and then qubit 0 is measured by the quantity and it goes to the output side Z value, right. So, the Z value actually measures the qubit 0 by using the Hadamard gate. Now, if you look at step number 5, another C0 gate basically controls qubit 0 and qubit 2. So, there are 3 qubits, C0 1 and C0 2. C0 1 tries to control 0 and qubit 1, and the C0 2 controls 0 and qubit 2. And the last stage is again you are measuring qubit 1. Qubit 1 means this is what you are measuring here, qubit 1, and that is being measured as x, right. Now, if the measurement, so these are the classical outcome x and z. So, if the measurement of qubit 1 equals to 1, we apply x gate because you do not want to change the state, and if the measurement of qubit 0 equals to 1, then you apply the z gate, right, and that is how you do the measurement. So, doing all these basics algorithmic stuff, we need to see that therefore, if you want to make all the logics which is available to us, for example, in this case bit 0 and bit 1, for example, for adding, for subtracting, designing a gray code, etc., we may require different types of gates, but not infinitely large number of gates. Typically, as you all know that in a classical computing you can actually use NAND and NOR gates for universal gates. But however, when you talk of quantum computing, in order to make different operations like qubit or creation of various states, you may require different states, different kinds of quantum logic gates, and similarly we cannot have indefinitely larger quantum states. Okay. All the quantum operations in bits can be approximated either by the Hadamard gate or the Toffoli gate, right, and this is known as the Solovay theorem, which is stated, also referred to as a universal quantum gate set, that all the quantum operation in a bit can be approximated by Hadamard and Toffoli gate, H gate and T gate, and all the operations can be actually approximated using this. So, let me again recapitulate what we did till now. Basically gave you an idea about the basic states of, so we looked into the basic gates available to us, and we looked into various types of gates on the Y, poly Y, Z, X, Hadamard, and we tried to see how these gates will do a transform of the qubits. But the idea is to make that from quantum state, which is totally indeterministic, to classical state where you have the fixed value of the output available to us. With this, I hope you enjoyed the lecture. For any queries, drop me a mail and we can discuss online as well, and I think we will meet in the next class. Thank you very much.